Imagine if I told you that our entire understanding of reality shifted completely, all because someone was trying to figure out why a piece of metal glowed. Crazy, right? Well, let's dive into this explainer and explore how one reluctant scientist's tiny idea shattered classical equations and gave birth to the modern quantum universe. Sometimes, the absolute most universe-breaking discoveries come from the most unassuming places. It feels like a massive leap. I mean, how does a single tiny idea spawn all of our incredible modern technologies? We're talking lasers, semiconductors, the smartphone sitting right there in your pocket, and even quantum computers. What's really wild is that the man behind this discovery didn't even set out to revolutionize science. He just wanted to solve a stubborn, kinda obscure puzzle about a glowing piece of hot metal. His name was Max Planck, and his discovery of quantum energy changed physics forever. Section 1. A flaw in physics, the hubris of the 19th century. To really understand this disruption, we've got to jump back to a time of immense scientific confidence. Back then, scientists thought Newton and Maxwell had pretty much solved the universe. But there was this one stubborn mystery that just refused to go away. And this mystery was deceptively ordinary. It's just heating up a piece of iron. Think about it. As it heats up, it goes through a really precise sequence of glowing colors. First a dull red, then orange, then yellow, and finally a brilliant, blinding white. Now, scientists could measure this light perfectly, but when they tried to actually explain this exact sequence using established classical physics, every single theory just completely failed. Which brings us to Section 2, the ultraviolet catastrophe, a mathematical dead end. Because you see, this failure wasn't just some minor miscalculation. To study this mystery, physicists used a conceptual model that they called a blackbody. Just imagine a perfectly black box with a tiny little hole in it. It's an ideal object that absorbs all incoming light and emits radiation based exclusively on its temperature. When they ran the experiments, they saw a very specific, consistent pattern of emitted light. So the experiential reality was totally clear, but the math? The math was completely broken. According to classical equations, as the wavelengths of the light got shorter, the emitted energy was supposed to increase without limit. The math basically dictated that a hot object should release infinite ultraviolet energy. Think about what that means. If classical physics were right, opening your oven door to check on dinner would blast you with a lethal amount of radiation. Clearly, that doesn't happen in reality. The experiments showed a very specific finite pattern. This absurd contrast between the math and reality became known as the ultraviolet catastrophe. Section 3. Planck's radical solution, the quantum leap. Enter Max Planck in the year 1900. Now, Planck was a traditionalist, but he had this bold willingness to follow the experimental data exactly where it led. He realized that if the old rules were giving an impossible answer, well, the old rules had to be wrong. To fix the math, Planck proposed something completely unexpected. What if energy isn't emitted continuously? What if nature actually releases energy in tiny, indivisible packets? He called these packets quanta. Instead of energy flowing smoothly like a continuous stream of water, Planck suggested it actually comes in tiny, distinct chunks. Here's a great way to picture it. Under classical physics, energy was thought of like a smooth ramp. You can stand at absolutely any point on that ramp, right? But Planck's quantum physics, it's like a staircase. When you walk up a staircase, you can stand on the first step, the second step, or the third step. But you can never, ever stand halfway between two steps. It's just physically impossible. Planck suggested energy works exactly the same way. Objects can only emit or absorb specific, distinct amounts of energy. And, boom, this insight instantly solved the mystery of blackbody radiation and laid the entire foundation for quantum physics. Moving on to Section 4, Einstein and the photon, validating the theory. Let's look at how this builds into an equation that would change the world, and how a young Albert Einstein stepped in to back it up. So, Planck discovered the simple yet profoundly elegant relationship, E equals hf. In this equation, E is the energy of one quantum packet, F is the frequency of the radiation, and H is a brand new number that tied the whole thing together, known as Planck's constant. It perfectly connected energy to frequency. And here is that number, Planck's constant, 6.626 times 10 to the power of negative 34 joule seconds. Now, to put that into perspective, that is a decimal point followed by 33 zeros. It is unimaginably, mind-bogglingly small, yet It acts as the fundamental building block that sets the microscopic scale for the entire quantum world. To grasp what this actually means in reality, we can look at how higher frequency light inherently carries more energy. Take radio waves, for example. They have a low frequency and therefore a low energy level. Visible light has a medium frequency, so it has proportionately higher energy. But things like X-rays and gamma rays, they have an extremely high frequency, so their energy is much, much higher. One elegant equation explains the entire spectrum of light and energy. Now, about 5 years later, Albert Einstein took Planck's mathematical framework and made a massive conceptual leap. See, Planck thought quanta were just how energy was absorbed or emitted by matter, but Einstein proposed that light itself is actually made of these indivisible energy packets. Today, we call them photons. He basically demonstrated that light isn't merely a continuous wave, but is actually made of quanta. Einstein used this concept to explain something called the photoelectric effect. Classical physics completely failed to explain why shining a super bright, intense red light onto a metal surface couldn't knock any electrons loose, while a very faint, dim ultraviolet light easily did the job. But using photons, the answer became obvious. Ultraviolet light has a higher frequency, meaning its individual packets carry enough energy to knock an electron free. Red light packets are just too weak, no matter how intensely bright the beam is. Energy depends on the frequency, not the brightness. This brilliant insight is actually what earned Einstein his Nobel Prize. Let's head into Section 5, the quantum world today, from theory to reality. Because it's really easy to look at black bodies and frequencies and write this all off as just some obscure 19th century puzzle. But I promise you, this discovery fundamentally matters to your everyday life right now. Today, Planck's discovery is literally everywhere. Quantum energy explains why atoms have stable structures. It's the underlying principle behind lasers. It's how solar panels convert sunlight into electricity. Actually, think about the device you're probably using right now. It is the foundational physics behind the semiconductors in our smartphones. Not to mention MRI machines in our hospitals and modern quantum computers. Every single one of these massive technological leaps owes its existence to Max Planck's insight. But the implications go way, way beyond human technology. The stakes are literally cosmic. Without quantum energy, chemistry as we know it simply wouldn't work. Stars wouldn't shine the same way. Life itself would be entirely impossible. So this wasn't just about building better electronics. It was about unlocking the absolute most fundamental rules of reality. Max Planck never intended to start a scientific revolution. He wasn't some rebel trying to upend the system. He was just a meticulous scientist who followed the evidence, even when it challenged everything physicists thought they knew for a fact. He birthed the quantum age just by trying to fix a stubborn math problem. It just goes to show, the biggest breakthroughs in human history often begin with the smallest ideas. In this case, quite literally the smallest possible packets of energy. So I'll leave you with this final thought. Put yourself in the shoes of a scientist back in 1900. If you were presented with this massive, universe-breaking paradigm shift, would you have believed that energy comes in tiny, discrete packets? Or would you have clung to the classical laws and thought it was totally impossible? It's amazing to think about how much our world has changed just because one person dared to trust the data over the consensus. Thank you so much for joining me for this explainer, and keep questioning the universe around you.